Okay, so this is lecture 15, and today in the lecture we're going to be talking about a sophistication in the grammar of predicate logic. So, in fact, actually, the name predicate logic, some people call it, instead of predicate logic, they call it relational logic, and we'll see today why they use that name. Now, in fact, actually, it's precisely the ability to represent relations and not just predicates that made the logic that was discovered at the end of the 19th century, beginning of the 20th century, why it was such a major advance over the previous logic. So it is true that the previous logic, the old logic, logic that was taught in European universities in the Middle Ages, it was not symbolic, but actually they were able to talk about things like subjects, predicates, and even quantifiers. What they didn't have a good grip on was the notion of how to represent a relation between two things. So we'll start today by learning, first of all, just how to translate sentences in natural language that mention relations into symbolic form. Okay, so we'll start here with a few examples. So these are just names here, so Maren and Niels. And the first sentence is Maren is taller than Niels. So the first thing we want to do here is we want to represent the names of people here by lowercase letters, as we were doing previously with just predicate logic. So we take, for example, the name Maren and represent it by a lowercase m, the name Niels, and represent it by an n. Now, what we were doing before, what we did in the last couple lectures, is we were talking about applying predicates to names. So we might write something like P, M if we were saying that Maren had some feature. So if we said something like Maren is tall, then we might say PM. P is the predicate, is tall. But now I want to say Maren is taller than Niels. So what we have here is this taller than, if you think of it like this, X is taller than Y. That's a relation that holds between two different things. And now we can plug in the names Maren and Niels. So we can say M is taller than Y. Sorry, M is taller than N. Maren is taller than Niels. Now we want to represent that is taller than in a compact form. And what we'll do here is, as before, we used a letter with a blank after it for a predicate. Now we'll put a letter with two variables after it for relation, where now the order matters very specifically. So here we're choosing for TXY means the thing in the first slot is taller than the thing in the second slot. So the final answer of the translation, Maren is taller than Niels, is TMN. Maren is taller than Niels, TMN. Okay, now if I put it the other way around, if I put TNM, that would say Niels is taller than Maren. If I put TMM, that would say Maren is taller than Maren, which of course is obviously false because no one's taller than themselves. Okay, but let's move on now. So where it's going to get interesting now is where we put in quantifiers together with relation symbols. So for example, Maren is taller than someone. Well, someone is not a name, right? You can't say, someone. It's not logically speaking a name. What we want to say is there is, so we're going to paraphrase this first. It says there is somebody such that Maren is taller than that person. So in other words, there is, the variable is arbitrary. I'm going to choose Y just because I'm kind of thinking, oh, the first slot of T would be an X and then Y. But the truth is the variable is arbitrary. So I'll put exists Y such that M is taller than Y. Maren is taller than someone. There is someone such that Maren is taller than that person. Okay. Now on to the next one. Someone is taller than Niels. Again, we paraphrase it as there is a person such that, but now the existential quantifier attaches to the first spot. So there is an X such that X is taller than Niels. There's an X such a TXN. Okay, we can go on now. So now we have a sentence that is has no names at all. So the sentence, everyone is taller than someone. Okay, so we need to sort of massage this into logic form. So everyone is taller than someone. So for all people, there is a person such that the first is taller than the second. Well, that's hard to say in natural language. It's easier to write in logic. Everyone, every X, there is a Y such that X is taller than Y. So everyone is taller than someone. And notice, by the way this is represented, everyone is taller than someone. What this actually says is for each person, there is a person. It might depend on the first person, the second person. For each person, there is some person that the first person is taller than. Okay, that's different than saying there is a person that everyone is taller than, because that would be nonsense. Okay, so let's go on to the next one. Someone is taller than everyone. That actually is nonsense, but we can represent that by saying there is someone such that every person, the first one is taller than the second. That's nonsense, because then that would mean the first person is taller than him or herself, which of course can't be true. But we can write it. It makes sense as a logical formula. Okay, so that's our first taste. Those last two slides were the first taste of a relation symbol. So TXY is a relation symbol. TXY, a relation symbol, when it has two places, needs either two names to make a sentence, or it needs a name and a quantifier. So in other words, both of those blanks have to be filled in order for it to make a sentence in some way or other, either with names or by attachment to quantifiers. Okay, now we're going to go on to slightly more complicated cases where we actually have relations that fit into complex formulas. Okay, so here's the first example here. There's a student that likes every subject. Now, in the previous examples, I was assuming that everything we were talking about is a person, but now I can't do exactly the same thing because subjects are not people. So some things here are people, some things are not. But I'm just going to take student to imply that it's a person. So in this case, there is a student, there's a person who is a student that likes every subject. Okay, so what I'm saying here is there is something that's an S. So in other words, I'm using SX for is a student. Now, here I have in this sentence, I have two other predicates and relations. I have two things. One's a predicate, one's a relation. I have a relation here, likes, X likes Y, and I'll use B for subject because I already used S for student. So I'll put BY for Y as a subject. Okay, so now what I want to say is there's a student such that that student likes every subject. So what I want to do is paraphrase that as, and for everything, if that thing is a subject, then that first X that we already named back earlier in the sentence likes the second thing. Okay, so in other words, what we have now is there is something that's a student, and for anything, if that thing, the second thing is a subject, then the first thing likes the second thing. There's a student that likes every subject. Okay, now let's try the second one. There is a subject that every student likes. Okay, here we have, again now, notice the variables X and Y aren't attached to students and subjects. Those are free floaters. We can use those in connection with whatever predicate we want. The important thing is, do we match them up the right way throughout the sentence? So I say there is a subject, there's a B, and anything that is a student likes that subject. Okay, so all in all, there is a B, there's a subject, and everything that is a student likes that subject. There's a subject that every student likes. Okay, now, next one. Every student likes some subject. Okay. This says something a little bit different, right? It says every student, anything that's a student. Now, let's be a little bit careful. Every student likes some subject. It does not say that everything is a student. It says anything that is a student has some feature. So in other words, for any x, if x is a student, then there is some subject. There is a subject such that x likes it. Okay, notice in the second phrase there, exists y, by, and lxy. It's an and because I'm saying there's a y and that y has two features. It's a subject, and that those students that we named, or that student that we picked out, that x likes the subject. Okay, so again, here we have universal gets associated. This universal gets associated with the if then. Existential here gets associated with the and. So for every student, anyone who is a student, there is a subject that that student likes. Okay. Good. So let's go on to some more examples like those. Okay, so we're going to start now with, so in many of these cases, in predicate logic, the one bit that is definitely an art in predicate logic, when you're looking at sentences that are in natural language, there's no necessarily one right way to translate that into predicate logic. In the cases I'm giving here, the examples, I'm choosing a way to represent it. In this case, I'm going to choose to take the basic relation here in these sentences to be, in the first case, a mother. So I'm going to say X is a mother of Y. I'll represent by MXY. Actually, let me rechange that to FXY just so I don't run into trouble with the small m that I'll use for Marin. So FXY will be X is, now I'm going to write a mother, although that's a weird way of speaking because the way we think, one can only have one biological mother. So we tend to use the phrase the mother of. So, but I'm just going to say here a mother of, because the point is they stand in that relation where the first is the mother and the second is the child or the offspring of the first. So now I want to say Marin is a mother, but now mother here is not a predicate, it's a relation. So what's actually being said when I say Marin is a mother is there is some child of Marin. Okay, also in this case, so saying Marin is the mother of someone or other. Okay, so there is some Y such that Marin is the mother of Y. So Marin is a mother. Okay. Okay, now, if we can now also take, in this case, we can take children, someone is a child if they have a mother, so to speak, in this case. So if I say Marin loves her children, what I'm saying now is for anyone, if Marin is the mother of that person, then Marin loves that person. So that says anyone who's a child of Marin is loved by Marin. Marin loves her children. Now, the truth is in English, it would be awfully weird. So this statement that I've just written in predicate logic for all x, if M is the mother of X, then M loves X, that actually would automatically be true of Marin if Marin had no children, okay? Because it says if somebody's the child of Marin, then Marin loves that person. So in other words, if Marin didn't have any children, the first part, Marin is the mother of that person, would always be false, which would make the conditional always true. So in English, the truth is if you say Marin loves her children, you kind of actually are implying that Marin has children. Now, we could, of course, just add that to this, right? We could say there is a Y such that Marin is the mother of Y, and anything that is the child of Marin is loved by Marin. Okay, so we could do that to capture the connotation in English. Okay, but let's go on to the next one. So every mother loves her children. I just showed you how to write Marin loves her children. So now we just want to change out the Marin and say that's true of every mother. So not just Marin. Okay, so we want to say every thing has the thing we just said of Marin. So everything has this feature. Okay, now the thing I just wrote is actually quite hard to read. It's not the way we think normally in natural language. It says for all y, for all x. If y is the mother of x, then y loves x, okay? But actually it turns out that that's equivalent, and we'll learn how to prove this later on in the course. It turns out that this is equivalent to saying that for all y, if there is something that is the child of y, then y loves that person. Okay, so anything that is the child of y is loved by y. Okay. Okay, so those are some examples of how we translate relation symbols. So as I mentioned at the beginning here, in general, the truth is we can have any number of places. So we have predicate symbols that have a single blank after them. We have now relation symbols with 2 blanks, and we could also have relation symbols with multiple blanks. So we could have one with 3 spaces after it, one with 4 spaces. Those would become more difficult to describe. But in any case, the order of the variables matters. And then also, as we've seen in some of these translations, the order of how you put the quantifiers out front can also matter as well.